you have any problem to conceptually understand this one. So basically, what we have talked about so far is that if I have a position function, and then we can think about velocity, that when I say velocity, it always means instantaneous velocity, right? And so that is denoted by s, and with this value st, if I have a formula and we can calculate the instantaneous velocity. How do you calculate the instantaneous velocity if I have a position function? Right, v, but that's a derivative, right? Derivative of st is instantaneous velocity. Okay? And all this thing, this st is a number, right? Okay? So it's a coordinate in one-dimensional shape. So either the particle is moving up and down like this in one-dimensional motion, or horizontally, or whatever the linear location is. The coordinate system is built on along this line. And we sketch this function a lot, and the graph, sometimes the graph of st, y equals st, here in t, sometimes the graph looks like this, right? And because it looks a lot like a projectile of something thrown in the air like this, but this is not a one-dimensional motion. Would you agree that this is a two-dimensional motion? Right? The things that are thrown in the air, not vertically, then it moves like this. But because the horizontal axis is t, this is not actually how the particle is moving, right? The particle is actually moving up and down, very simple. Not two-dimensional, it's just one-dimensional. Repeat the path and up and down. So don't kind of confused whether this is the actual projectile. Actually, how it's moving is one-dimensional motion. You enter two-dimensional motion at the end of the Calc 2 and in Calc 3, and that's where you enter. Make sure everything we do here is really the one-dimensional motion. Particle going up and down, car going back and forth. No more complicated than that. All right, so I just wanted to clarify that here's a new thing that I think I already introduced it. Position, this idea. Position is easy to accept, that there is this thing in the physical world is located in a certain place. And then a little bit of time later, it is somewhere else. So it tells you average, the idea of the average velocity and all that, right? So but velocity is not marked like this, right? Velocity is kind of our abstract idea. But we understood and managed to calculate that. But velocity also changes, right? Velocity changes. If you think about dropping something in the top of the building, and because of the gravitational acceleration, it moves faster and faster. When you start a car, you have a tendency to go faster and faster to a certain speed, right? So the velocity changes. So we feel that whole thing, but it's not easy to visualize. But we have this automobile that many people drive, and that is its kind of idea. This is actually the position. Then we can visualize the velocity. Let's say there is this speedometer, very unusual speedometer. So it's not a circular needle. It is actually the vertical bar. So let's say if your car has this one, it's showing the dot is your velocity. When you start the car, the dot is moving faster in here, right? So you can change the idea of the velocity to a position again. Does that make sense? So you can see that dot, this weird-looking speedometer in your car, the dot is moving, forward, backward as you go faster and slower. So although velocity is not a position, you can turn that into a position of dot that you see in the speedometer. So you can apply it again. How fast this dot is moving, right? The position of that needle in your speedometer, how fast it's moving around. So you can think about the speed again, the instantaneous rate of change of velocity. Some people, that's natural, that's easy to understand. But if not, I try this. Okay? If the instantaneous rate of change of the velocity is difficult to understand, then think about the velocity to turn into a position in your speedometer, and think about that dot moving back and forth really quickly. So what is the instantaneous rate of change of that dot? The position of that dot, the particle. And that's the instantaneous rate of change of the velocity of the actual moving vehicle or particle. Does that make sense? If you have a position function, how do you go to instantaneous rate of change? You differentiate it again, right? So the mechanical is very simple. You just have to understand the conceptual thing. So if at the beginning, when you start the car, usually your needle moves really fast, right? So instantaneous rate of change of velocity at the beginning of the when you start a car is fast, but when you reach 60 and 70 miles, it slows down and you don't change the velocity that much, right? So a moment later, the instantaneous rate of change of velocity is usually close to zero, right? Things like that. Does that make sense, the idea? Mechanical is very simple. So here is the position. What I mean by mathematical mechanism, that's what I mean by mechanical. St is a position function, right? Then what is the velocity? It's denoted by S prime t, right? That we have thought of, learned how to mechanically calculate S prime t using the product rule and the quotient rule and all those rules, right? If the position function is given. Now we're interpreting this velocity as a dot in the speedometer, and think about this instantaneous rate of change again. What is the physical term that describes instantaneous rate of change of the velocity? Acceleration. Now it's a notation. If you differentiate one more time, they wanted to use this double prime notation as prime of t. There is if you have function as t, you can imagine you can calculate as prime of t. That's another function, right? And you apply the derivative one more time to that. You can certainly do that, and that has an important meaning in physics: acceleration. Okay, and you can continue differentiate, right? You can instantaneous rate of change of the position of the instantaneous, whatever that meaning is, mathematically is just simple. You just keep differentiating, correct? So you can go and triple prime like that, how fast this acceleration is changing. The physicist, Newton, was the person who put down the notion of acceleration where the force is exerted to the moving object. So it's easier if it's a force, everybody feels a force, and how much of the force is changing is next move. Okay? So yeah, I think you're pushing it, and all of a sudden, and you're pushing it harder, and it's kind of jerky motion. Is if you feel that the jerky motion, and there is this right, the force is changing. So that's the instantaneous rate of change of acceleration. Implies that there are some forces additionally applied and not applied, and things like that. So that could be the meaning, jerk, that is a term. But mathematicians, why not? You just keep, from here they don't use the primes anymore. They use this notation. 4 in the parentheses up there is not fourth power. It's 4 times differentiated. And a t. I don't know if there's a physical term that describes that, but the mathematicians just keep doing that. And amazingly, that you will learn this at the end of the Calc 2, that all this, the values of a derivative, has amazing application in analyzing transcendental function. And physics usually stops here and rarely go to the jerk, and mainly the classical mechanical. Classical mechanics is all about these 3 functions. In mathematics, they keep going, and they show you how wonderful this information can be used to do fantastic things. So there is application to these higher derivatives, and it's denoted like this. Okay? So you can write it